Our next speaker is Dr. Kevin Grazier, and he works with NASA's Jet Propulsion Laboratory, as well as a very impressive background that he'll have a chance to share with you. And he is going to be challenging us with this simple question: are we alone in the universe? And if yes, where does that search begin? It's an exciting topic, and I welcome Dr. Kevin.
The honor of acting as the science advisor for 4 seasons of Battlestar Galactica, and currently working on the 4th season of the show Eureka. So, glad we have some fans. And today's talk might seem like it's going to border on the nebulous area between science and science fiction, because are we alone is a question that we've been asking as long as people have been looking up in the sky and recognizing that those stars might be someplace a little far away. And the science fiction author and scientist Isaac Asimov once said, "Sometimes I think we're alone in the universe. Sometimes I think we're not." Either way, the notion is quite staggering. And when you think about it, and if you do start thinking about it, you will lie awake at night, it is kind of staggering either way. Earth, that's our home. And there's a reason why we're here. There's a reason why we have life, and you're looking at it. Water. We have the oceans, we have clouds, we have ice, we have lots of it. And the start of the search for is there life out there begins with a search for liquid water. We have plenty of it. And although all life forms on Earth, all living things need food, they need air, they need water. Well, we eat different foods. Everything here eats something different, ranging from the Ebola virus to Albert Einstein. I don't think Albert's eating a whole lot these days, but everything else here might still be consuming food. Things extract different gases from the atmosphere. Plants inhale, and they extract CO2. We inhale, we extract O2, but we all drink H2O. Water is water everywhere, and that is the basis upon which life is formed here on Earth. So we begin our search out there for places, abodes, where we'll find liquid water, and we're finding that water is a lot more common than we'd previously thought. It's common around here, obviously. Even though we're in a desert environment, we're surrounded by it. And speaking of desert environment, we're a little wetter this year. We are having an El Nino event this year, a mild one. That big blob of water is a big blob of warm water that's just off of Central America. Makes it a little rainier. I know it rained where I live this morning, so it's a little wetter this year, even in our desert. But there are other deserts in the solar system. Venus. Venus is on the inner edge of what we call the Goldilocks zone in the solar system. The Goldilocks zone is the area, or the distance from a star, where the temperature is not too hot, it's not too cold, it's just right for the formation of liquid water. Venus is on the inner edge of this, but it has a thick atmosphere made of carbon dioxide. Now, you often hear planetary scientists say, we study other planets to learn more about Earth. Now, is that really true, or is that what we tell Congress when we want more money? Well, the greenhouse effect has been on the news quite a bit lately. Wasn't discovered here, discovered there, on the planet Venus. We discovered the greenhouse effect from its 96% CO2 atmosphere and realized, hey, that happens here. And in fact, the greenhouse effect kind of gets a bad rap, because without the greenhouse effect, we wouldn't be here. Our planet would be too cold. So it does trap enough heat to keep us warm that we're here, but hopefully we don't trap too much heat that other unfortunate things happen. Venus is too hot. Because it has such a thick atmosphere, its temperature is about 900 degrees Fahrenheit everywhere across the planet. Since water boils at 212, that means what little water is here is gas, pure gas. Let's look at the other end of the Goldilocks zone, another neighbor, Mars, a cold desert. No water here. Well, there actually is. The atmosphere is either very wet or very dry, depending on how you look at it. There isn't much atmosphere, but what little atmosphere there is 100% saturated. It's 100% humidity here on Mars. Now, we've known water exists on Mars for some time, because for decades, almost a century, we've known that Mars has polar caps. So we know there's ice at the poles. Does that mean that there's an atmosphere conducive for life, or an environment conducive for life? Well, the Viking spacecraft, the twin Viking spacecraft, explored Mars back in the 1970s. I teach class at UCLA and Santa Monica College. I find most of my students do not realize that we, NASA landed on Mars twice, successfully, all the way back in 1976. Pretty exciting. The twin Viking spacecraft were themselves twin spacecraft. Part was an orbiter, part was a lander. The landers each had arms that could reach out, scoop up soil, and split that into experiments to see is there life in the soil. These are images taken from Mars. No, that's not the painted desert in Arizona. And what did they find? Well, the experiments on board were inconclusive. Most scientists would agree that they said no, but one of the experiments actually said yes, and some scientists argue quite vehemently that that said there's life on Mars. All scientists say it's inconclusive. The results from these experiments were probably negative. We realize that science sometimes is done by trial and error. Not trial and error, but so much that you learn from your mistakes, and we learned that back then we didn't know how to look for life perhaps as well as we do now. We did find evidence of water on Mars. Evidence of flow, evidence of channels, or of outflow channels, evidence of beds, evidence of permafrost. This type of crater here, called a splosh crater, is a hint that there could be ice, permafrost, underneath the soil. So if there was water on Mars in the past, as suggested by the evidence of flow, it could have either evaporated off into space or could have sank into the ground. These splosh craters were evidence it sank into the ground. Now, that was back in '76. In the interim, we've learned a thing or two. In fact, Dr. Ken Nielsen studies extremophile life, extreme loving life here on Earth. And he said, if you haven't taken biology in the past 10 years, you haven't taken biology. In our search for life, not only are we expanding the places where we can look, we're also expanding our notion of where life can thrive and what life is. For example, we all learned way back when, that the sun is the basis of the food chain, right? The plants absorb the sun, things eat the plants, things eat the things that eat the plants, et cetera, et cetera. Then they die into the soil, the whole circle of life. We could all start singing. But that's not entirely true anymore. We've learned a lot. The deepest parts of our ocean are what are called subduction zones, where one oceanic plate is being thrust under another oceanic plate or a continental plate. We have the deepest parts of the ocean. Very deep trenches. There's the Peru-Chile Trench, the Japan Trench, the Marianas Trench, 7 miles deep. When we look in these trenches, these are high heat flow environments. Water percolates into the rocks, is heated by the subsurface, and comes shooting back up in these vents. And around these vents that are called black smokers, we find life forms that are completely different than any life on the planet. Their chemistry is different, and this life around here is based on Earth's internal heat. If you attached a lamp cord to the sun and went click, turned it off, we'd get sunlight for about 8.5 minutes, speed of light, and then Earth would start to cool. The oceans and seas would freeze. The very bottom of the ocean, where these thermal vents are, wouldn't know anything happened. They would just continue to thrive like nothing, like yesterday. It would just be the same. So we have deep ecosystems based on Earth's internal heat that do not need the sun. Further, in studying other forms of life, remember Jurassic Park? Remember the character Ian Malcolm, Jeff Goldblum's character? He said, life will find a way. We're learning that life thrives in extremes of heat, cold, salinity, acidity, extremophiles, extreme loving life forms. This is Old Faithful, and this is a geyser, or sorry, this is a glacier. In Yellowstone Park, you'll see some of the hot springs, the hot pools, that have concentric rings of different colors. Now, if you dissolve enough minerals in water, you can heat it to either well below freezing, what we call freezing, or well above boiling. This water would scald you to death almost instantaneously. It's very, very hot. The concentric rings correspond to different temperatures. The colors correspond to different life forms that like those temperatures. All this water is well above what we consider boiling, yet these things thrive in it. So we're finding life that loves the heat. We also find life that loves the cold. These are ice worms. They're worms that live in ice. In glaciers. So these things have antifreeze for blood. If you raise them to 5 degrees Celsius, they melt. No kidding, they will melt. So we have things that love extreme of heat, extreme of cold, expands our notion of where we might find life. And the fact of the matter is water, at least in the form of ice, is not uncommon in the solar system. This is a moon called Enceladus. It is almost entirely water ice. When you go to the outer solar system, most of the moons, with a few exceptions, are water ice, at least on the surface. How you define a rock depends where you are in the solar system. In the outer solar system, a planetary scientist considers ice to be a rock. It is a main solid component of many of these moons. This is Europa. Now, one thing you'll notice that will leap off the page at you for Europa is that there's a dearth of craters here. Our moon is very cratered in the highlands. Most planetary objects are cratered. Europa is not. What a crater count tells you is the age of the surface of an object, not the age of the object itself. Everything is pretty much 4.6 billion years old. But the surface is young. It's been resurfaced. Earth has few craters because we have wind, we have volcanism, we have tectonism. Things like craters get erased. And obviously, something's erasing whatever impact craters are on Europa, except for this one right here. Up close, we see fractures that look like Earth's mid-ocean ridges, where the convection in deep Earth is pulling the crust apart. New material wells up, gets pulled apart, wells up in a cycle. This looks like the mid-ocean ridges on Earth, implying, at least initially, that there might be some kind of convection. What convects? Liquids. So, is there a subsurface ocean here? That's the question we asked, and all measurements seem to indicate there's water underneath Europa's icy crust. Here's a place, lots of water, warm enough that we could potentially have life. So our notions of where we're looking for life out there is evolving. So our understanding of the environments in which life can thrive is expanding. At the same time, our notion of the environments in which that could have life is expanding. We're now considering in the future sending missions to Europa that will have ice-penetrating radar to verify that ocean, and then maybe aquabots that will melt through the ice and zoom around on the subsurface, looking for thermal vents, looking for the European equivalent of our deep-sea thermal vents. On Mars, we have several spacecraft that have pretty much confirmed that Mars was warmer and wetter in the past. Global Surveyor was at Mars for 7 years, and it took images like this. Now, if you said that was Utah, I'd probably buy into that. But it's actually layered deposits, sedimentary rock on Mars. This kind of rock is formed where you have large amounts of standing water. So in the past, we've had flowing water and standing water. And we have a reminder that I have to do a TED Talk. We have evidence. Remember the crater before I said was evidence that water had seeped into the ground. Evidence of water flowing out of side of hills. Evidence of water flowing out the sides of craters. Evidence of water flowing out the side of canyons. Evidence that water seeped in the ground and froze. Mars Odyssey was a spacecraft that had a sensor that could sense water or ice in the upper meter of Martian soil. Long story short, if you took Mars, heated the upper 1 meter Mars wide, you would get enough water to fill Lake Michigan twice. So we know there's plenty of water on Mars. Spirit and Opportunity, our two rovers, were sent to places where we believed water existed in the past. This is Gusev Crater, where Spirit roamed, and, well, we believe it's a crater. It was filled in with water because we have a channel leading into or out of it. But both have found minerals that exist or formed only where you have standing water. So we verified that there's been standing water on Mars in the past. It was warmer, it was wetter, it had, for a while, at least, an environment conducive for life. What about today? That's still TBD, but we're looking. Mars Reconnaissance Orbiter. This spacecraft is currently at Mars now. It has a camera so sensitive it could see a beach ball on Mars. It has seen deltas on Mars from the past. Mars Science Laboratory, launching next year, it's the size of a Mini Cooper. And it has devices on it different than Viking that will scoop up soil. If there's life in the soil, if there's been life in the soil, if life went to the bathroom in the soil, we'll find it. At the same time, these aren't the only places we're looking. This is the spacecraft on which I work, the Cassini-Huygens mission, that has been at Saturn since 2004, July 1st. And this is one of our targets, Titan. Largest moon of the Saturn system, second largest moon in the solar system, larger than the planet Mercury. If this were in orbit around the sun, not Saturn, there would be no is Titan a planet debate. It would be a planet. It has a thick photochemical haze. It has an atmosphere, and it has a thick haze that we have a hard time seeing through. The Voyager spacecraft couldn't see through it. The good news is Los Angeles now no longer has the title of smog capital of the solar system. That belongs to Titan. But with instruments on Cassini, we can peer through that and see through to the surface below. We found lakes of hydrocarbons, lakes of ethane and methane. The surface is ice. We have found volcanism. Now think, if the surface is ice, there's volcanism, that's melted rock. If rock is ice, lava is water. So we've seen evidence of volcanism. We've seen what may be a plume, might have been an eruption. So a magma chamber could be a big cauldron of liquid water. That's sci-fi only a few years ago. A big magma chamber on a moon of Saturn could be a cauldron seething with life. But it's something we've considered. We also now believe that Titan, like Europa, has an ocean of water beneath its icy crust. Then there's Enceladus, this little moon that's only 500 kilometers in diameter, that's 300 miles, in case you thought JPL is incapable of converting units. It has geysers that launch ice crystals out into space, creating Saturn's outermost ring. These geysers, to exist, require the presence of liquid water in the subsurface, almost certainly. So we have evidence of liquid water existing on a very tiny moon of Saturn. Right now, this is what would look like were you walking on the surface of Enceladus. Well, you've heard that Europa is a place where we're considering as a abode of life. Enceladus, we've actually measured the water there. So a tiny moon of Saturn could be another stop in our search for answering the question, are we alone? Well, it turns out that water is not uncommon in the solar system. Many of the moons in the outer solar system are made of water, ice. Really, we're just getting started. The search for are we alone, that age-old question, begins with a search for water. Our understanding of life, our understanding of abodes is expanding, so we're really in our infancy. Stay tuned.